Hello and welcome to the fourth lecture of this module micromechanics of lamina. So, in our last class we have discussed the determination of longitudinal tensile strength of a lamina, wherein it was assumed that the longitudinal tensile strength of a lamina is decided by the fiber failure only. So, if you look at this this stress strain curve we have discussed in the last class. So, when the fiber fails, that means at this point when the strain in the fiber reaches the ultimate strain of the fiber, then the composite fails, and based on that we have derived a relation for the longitudinal tensile strength of the fiber, and of course, it is dependent on the fiber and matrix properties, strength and stiffness properties and volume fraction. Therefore, for a given properties of the fibers and the matrix, basically say the Young's modulus and the ultimate strength properties of a fiber and matrix, for a given fiber and matrix, it is the volume fraction which decides what will be the the fiber volume fraction which decides what will be the longitudinal tensile strength of a lamina. So, we try to understand that how the volume fraction actually influences the longitudinal tensile strength, and we could also see that there is a critical volume fraction. We have discussed in the last class that the slope of the stress strain curve for the lamina or the composite will be decided by what is the volume fraction. Okay. For a given properties of the fiber and matrix, higher is the volume fraction V f, more it will be inclined towards the fiber stress strain curve, and lower is the volume fraction, more it will be inclined towards the matrix stress strain curve. And we could see that if the volume fraction is actually more than a critical volume fraction, then only it is ensured that the longitudinal tensile strength of the lamina will be higher than that of the matrix. If the volume fraction is less than the critical volume fraction, then the longitudinal tensile strength of the lamina will be less than that of the matrix, and the objective is not served. Okay. We have also seen that there is a minimum volume fraction. If the volume fraction is below minimum, then even if a fiber breaks, the matrix remaining matrix could actually withstand the load. Therefore, we understood the influence of volume fraction in the longitudinal tensile strength of the lamina or the composite. In all this, we made certain assumptions. One of the key assumptions in determination of this longitudinal tensile strength is that the fibers are of uniform strength. That means, all the fibers are having the same strength. That means, all the fibers in a lamina break or fail at the same time. We can clearly understand that does not, this assumption does not go well with the practical composites. Therefore, there will be deviations in the predicted strength, okay, from the actual longitudinal tensile strength. There are some other assumptions also made in determination of this strength parameters as well as stiffness parameters using micromechanics approach, and we will have to be, while some of these assumptions do not go well with the practical situations, therefore, there will be deviations, while some of these are significant, some of them may not be very significant. Therefore, we must understand the factors which actually influence the strength of a composite, okay, strength of a composite or lamina in particular. So, some of the important factors are fiber orientation. If you remember, we actually assumed the perfectly aligned fibers. Okay. Now, you know that the strength of the fiber is, the longitudinal strength of the fiber is much higher compared to the transverse strength. Therefore, in a lamina, when we have the fibers aligned along the direction of loading, we will get the maximum strength. Compared to that, if some of the fibers are not aligned, suppose there is misalignment, suppose some of the fibers are not aligned, there is misalignment, that will actually affect the strength of the composite. Now, how much that deviation will be, that is decided by the number of fibers which are misaligned and the degree of misalignment. Okay. Then just now we have discussed that the strength of the fibers are actually not uniform, even though an assumption has been made in the micromechanics model that the strength of the fibers are uniform, but it is not so. Actually, the strengths are statistically distributed, and therefore, that also affects the longitudinal tensile strength of the composite. Say for example, suppose we are take an example that you have in a lamina, just for the sake of example, there will be a large number of fibers. Suppose we are considering only 3 fibers. This is 1, this is 2, and say this is another fiber. Okay. Suppose there are only 3 fibers. Okay. Now, subjected to load, suppose one of these fibers actually breaks. Okay. Then what happens? Initially, all these 3 fibers are actually sharing the load. Now, because this fiber is broken, so this is not taking part in the load bearing anymore. Therefore, the load is shared by the 2 fibers. Suppose initially the load in each was say F by 3. Now, the load in that 2 intact fibers will be F by 2. Therefore, the fibers, adjacent fibers which are intact are actually overstressed, and as a result of that, the chances of the failure of those fibers become higher, and so suppose next another fiber fails, and therefore, the remaining fibers are even more overstressed. So, this is how the cumulative fiber breakage takes place, and the actual tensile strength of the lamina will be less than that has been predicted with the assumptions that the fibers are of uniform strength. Now, when the fibers are of non-uniform strength, I mean the weakest fiber will obviously fail first, and then once that fails, the other next weaker most fiber will fail. So, this is how the cumulative fiber breakage takes place. So, the non-uniform fiber strength actually influences the strength of the composite. Okay. Then discontinuous fibers, like we have assumed that all the fibers are continuous. Make note of the fact that in a lamina, this is a continuous fiber. Okay. Suppose the fibers are not continuous, suppose there is a discontinuous fiber. Okay. When we apply load, the load is applied on the matrix, and this is transferred to the fiber by the edge of the fiber, and there is a stress concentration at that point. Now, if the zone of stress concentration is far less compared to the length of the fiber, we can consider that the fibers are of infinite length. Okay. Otherwise, for short fibers, this has to be taken into account, and that influences the longitudinal tensile strength of the composite. Then interface, we assume a perfect interface. We will appreciate that the interface between the fiber and the matrix. Okay. Suppose this is the fiber and this is the matrix. The interface between the fiber and the matrix plays an important role. Stronger is the interface, stronger is the composite. Okay. Now, what happens is, if the interface is weak, then the transverse crack, which sometimes gets induced in a composite, propagates through the interface, leading to the degradation of the strength of the composite. For example, what is transverse strength? I think you can understand that. Suppose you have a lamina. Suppose this is the fiber, this is the matrix, and this is the fiber. Suppose we apply transverse load, then what happens? Under transverse load, sometimes the matrix cracks. Okay. If there is a matrix crack, now this crack, when it encounters the fiber, it cannot penetrate through the fiber, because fibers are very, very strong. It has a high longitudinal strength. Therefore, this crack actually propagates to the interface. So, for a weaker interface, it propagates through this fiber matrix interface, and then the failure takes place, thereby reducing the overall strength of the composites. Okay. Then residual stresses, we have discussed that the residual stresses are induced in the lamina because of 2 reasons. Number 1, the mismatch in coefficient of thermal expansion, and the fabrication temperature is different compared to the operating temperature. Because the mismatch of the coefficient of thermal expansion, the residual stresses are induced. We have discussed these things in details earlier. Residual stresses are induced in the fiber and the matrix, and these residual stresses get added to the stresses applied by the mechanical loading. When a composite or a lamina is loaded, the stress gets added to the residual stresses, and thereby the strength of the composite is reduced. Therefore, these residual stresses should be taken into account while analyzing the strength of a laminated composite. Okay. So, we understood in the last class the determination of longitudinal tensile strength of a lamina. So, let us discuss the transverse tensile strength. Okay. Now, unlike the longitudinal tensile strength which is entirely almost entirely decided by the fiber properties, okay, the transverse tensile strength is also actually influenced by many other factors like bond strength of the interface, presence of voids, then internal stress strain distribution, of course, in addition to the fiber matrix properties. Okay. Now, it is observed that the transverse tensile strength of a lamina or a composite is actually less than that of the matrix tensile strength. Okay. That means, addition of fiber actually have a negative effect on the transverse tensile strength. Okay. Now, a simplest way to determine the transverse tensile strength is to assume that transverse tensile strength is due to the failure of the matrix, okay, in the by the tensile stress. So, a simple model for determining, so considering this RV, we consider this we have done earlier also. Consider an RV having fiber diameter d and the fiber spacing as S. Therefore, this is the fiber, this is matrix, it is a single fiber RV. Okay. And the stress applied in the direction 2 is sigma 2. Okay. Suppose the transverse deformation of the composite is delta c, transverse deformation of the composite. Similarly, delta f is the transverse deformation of the fiber and delta m is that for the matrix. With usual assumptions of perfect bonding, uniform fiber spacing, fiber matrix, both fiber matrix and the composites all follow Hooke's law, that is linear elastic, and no residual stress. Okay. Now, the total transverse deformation of the composite in this RV must be equal to the transverse deformation of the fiber and the transverse deformation of the matrix. Okay. Now, suppose epsilon c, which is nothing but the strain in direction 2, is the transverse strain of the composite. Transverse strain in composite. Okay. Transverse strain induced in the composite. Epsilon f is that induced in the fiber and epsilon m is that induced in the matrix. Now, looking at this RV and going by the definition of the strain, we can write the expression for strain epsilon c is equal to change in length delta c by original length, okay, S. Epsilon f is equal to delta f by d. These are all transverse strain. Okay. Epsilon m is equal to delta m by S minus d. Okay. So, this is 2. So, putting in 1, we have 1 was delta f is equal to, sorry, 1 was delta c is equal to delta f plus delta m. If we put this 2 here, we get So, delta C is equal to S epsilon C, delta F is equal to D epsilon F, and delta M is equal to S minus D epsilon M. Okay. So, dividing both side by S, we get epsilon C is equal to D by S plus 1 minus D by S into epsilon M. So, this is nothing but the transverse strain epsilon 2, which is equal to D by S plus 1 minus D by S into epsilon M. Okay. So, this is what we get. This is the transverse strain in terms of the relative dimensions of the, sorry, this is epsilon F, epsilon F. Okay. Now, suppose the strain, the stress in the transverse direction is sigma 2. Now, sigma 2 is nothing but sigma F is nothing but sigma M. I mean, this is the composite stress, which is the transverse stress, because this is the stress is in this direction 2, and the force divided by this cross section, whether it is here, whether it is here, whether it is here, it is same. Okay. So, uniform stress, of course, with the assumption that the fibers are equally spaced in the thickness direction. Okay. So, stresses are same in the transverse direction in the fiber, matrix and the composite. Now, with the assumptions that we have that the fiber, matrix and the composite obeys Hooke's law. Okay. So, we have sigma F is equal to epsilon F into E F. Okay. This is equal to sigma M is equal to epsilon M into E M. Okay. So, this is our equation number 3. Okay. So, from this we can write that epsilon F is equal to E M by E F into epsilon M. So, this is your equation number 4. Now, 3 and 4, putting 4 in 3 implies epsilon 2 is equal to D by S E M by E F epsilon M plus 1 minus D by S epsilon M. Okay. And therefore, this could be written as epsilon 2 is equal to this. So, this is our equation number 5. So, we could obtain an expression for transverse strain in the composite in terms of the transverse strain in the matrix, the modulus of the matrix and the fiber, and the relative spacing SD, which is relative dimensions of the fibers and the matrix. Okay. Now, if we assume that the transverse failure of the composite is due to the failure of the matrix, meaning that at failure the strain in the matrix epsilon M is equal to ultimate strength of the matrix. That means, in the transverse direction, when it is loaded in the transverse direction, we obtained the transverse strain in terms of the transverse strain in the matrix and the other modulus and the spacing D and S. Now, if we assume that the failure is due to the matrix, then at failure sigma M must reach the ultimate strength of the matrix. That means, if this is the condition, which means the composite strain in the transverse direction at that point is nothing but transverse tensile strength. Okay. So, from the last equation, that means equation number 5, we can now write, we can replace epsilon m by epsilon m u and epsilon 2 as epsilon 2 T u. Therefore, we can write epsilon 2 T u is equal to d by s E m by E f, okay, plus 1 minus d by s into epsilon m u. Okay. So, this is the expressions for ultimate transverse tensile strain of the composite in terms of the ultimate strain of the matrix. Okay. So, this is our equation number 6. Therefore, again the composite also obeys Hooke's law. Therefore, we can write the transverse tensile strength of the composite is nothing but E 2 into epsilon 2 T u, okay, because the composite also obeys Hooke's law. Therefore, when it is loaded in the transverse direction, suppose this is epsilon 2, this is sigma 2. So, at failure, suppose this is the failure point, this is nothing but epsilon u, which is actually sigma u divided by E 2, because it is loaded in the direction 2. This is nothing but E 2. Okay. Therefore, we can write sigma T u is equal to E 2 into d by s E m by E f plus 1 minus d by s epsilon m u. So, this is what we get. Now, what is this E 2? Already we have the expressions for E 2, where this is equation number 7, where E 2 we obtained using mechanics of material approach is equal to V f by E f plus V m by E m, which implies E 2 is equal to E f E m by V f E m plus V m E f. Okay. Therefore, we get sigma 2 T u is equal to E f E m V f E m plus V m E f into d by s E m by E f plus 1 minus d by s epsilon m u. Okay. So, this is the expression for transverse tensile strength of a lamina in terms of the strength of the matrix and the Young's modulus of the fiber and the matrix and the volume fraction. Okay. Now, we can, this is a simple model where we have assumed that the transverse tensile failure of the lamina is because of the strain in the matrix reaching the ultimate strain of the matrix. Okay. Now, as we have discussed earlier, see the, now if you see that in the case of E 1 or in the case of sigma 1 T u, actually the presence of fibers led to the improvement in the longitudinal modulus as well as longitudinal tensile strength. Of course, if the volume fraction is kept above certain critical volume fraction that leads to the improvement in the longitudinal tensile strength. Also E1, that is the longitudinal Young's modulus is of the composite is more than that of the matrix by adding the high modulus fibers. Okay. Even in E2, even in the case of E2, the E2, that means the transverse modulus of the composite is more than that of the matrix, because the presence of the high modulus fibers actually puts constraint in the transverse deformation, thereby increasing the transverse modulus. But in the case of transverse tensile strength, actually the presence of the fibers lead to induction of stress concentration in the matrix, and thus the strength of the composite is actually, the transverse tensile strength of the composite is actually less than that of the matrix. So, the presence of the fibers in the case of transverse tensile strength is having a negative effect. Okay. Say for example, if you see for a graphite epoxy, the transverse tensile strength is only 40 megapascal, whereas the longitudinal tensile strength is 1200 megapascal. This is the reason is because under transverse loading, the cracks actually nucleate in the transverse direction, and it propagates through the fiber matrix interface. Okay. Also there is debonding of the fiber matrix before the matrix fracture. Okay. Like if you have a lamina, suppose this is the lamina, this is the fiber, when it is actually loaded, there may be transverse crack in the matrix. Okay. There may be transverse crack in the matrix, and this, once this crack reaches the interface, it actually propagates through the interface and thereby reducing the transverse strength of the composite. So, the net result is that the transverse strength of the composite is less than that of the matrix, and it is sometimes written as sigma to Tu is sigma m u divided by S, where S is the strength reduction factor and is given by this, okay, which is a function of the Young's modulus of the matrix, Young's modulus of the fiber, and volume fraction. Okay. Depending upon what is the ratio of Em by Ef and the volume fraction, the strength reduction factor could be obtained. Now, for some values it could be maybe 2, that means the strength of the transverse tensile strength of the composite is half that of the matrix. Okay. Next, so we understood the longitudinal tensile strength and transverse tensile strength, and next is the longitudinal compression strength, compressive strength of a composite. Okay. Now, the models we have actually used for tensile strength may not be suitable for longitudinal compression strength, because in under compression the failure modes are different. There are 3 possible failure modes. Number 1, transverse tensile, suppose a lamina is actually, suppose a composite is subjected to compression. Okay. So, there are 3 modes possible. One is transverse tensile failure, I will come back to that, then micro buckling of the fibers and shear failure of the fibers. Okay. So, transverse tensile failure is the under this loading, when it is subjected to compression, when the composite is subjected to compression, therefore, there will be, it will experience tensile strain in the lateral direction. Okay. And due to this tensile strain in the lateral direction, the matrix might fail, or there may be fiber matrix debonding. Okay. Then there are micro buckling of the fibers, that means suppose you have a, we have a composite where there are fibers and it is subjected to compression load, there may be localized micro buckling of the fibers. So, I am just exaggerating, maybe at this point the fibers may buckle like this, even though there is no gross buckling of the laminate or the lamina. Okay. There may be localized micro buckling of the fibers. Now, depending upon the volume fraction, if the volume fraction is very less, very low, the fiber micro buckling may take place even at a much lower level of stress, whereas with a practical volume fraction of say maybe less than more than 40%, the fiber microbuckling many a times actually is preceded by the fiber matrix debonding. Okay. So, what might happen is, suppose there are two fibers, they might buckle and thereby putting the matrix in between under tensile stress. Okay. This fiber microbuckling may be in the extension mode like this, or two fibers may buckle cooperatively, thereby putting the matrix under shear. Okay. This is extension and this is the matrix is in shear. Okay. So, therefore, the simple models which we have used for determination of transverse tensile strength, or I mean for the longitudinal tensile strength, could not be used for determination of longitudinal tensile strength. However, just to understand a simple model based on the ultimate tensile strain of the matrix, suppose we take a lamina and it is subjected to a compression stress sigma 1 in the direction 1, which is the principal material direction, and naturally because of that there will be transverse strain. So, this is the longitudinal strain, okay, where U 1 is the longitudinal Young's modulus of the composite, and because of that there will be a transverse strain which will be tensile if the stress is compressive in direction 1. So, the strain in the direction 2 will be tensile, and this is because of the Poisson's effect, and this is what is the transverse strain in the direction 2. Okay. Now, at failure, suppose under this compression stress along direction 1, suppose it fails, therefore, at failure if the failure is because of the transverse tensile failure of the matrix, then at failure the composite will fail when the transverse strain reaches the ultimate transverse strain of the composite, which is given by this epsilon T u. Okay. And the corresponding compression stress sigma 1 at that point is nothing but the sigma 1 C u, that means the longitudinal compressive stress. Okay. Therefore, we can write this equation as at failure we can write this, that when the epsilon 2 reaches epsilon 2 T u, sigma 1 is nothing but sigma 1 C u. Okay. And from this we can have an expression for sigma 1 C u in terms of epsilon 2 T u, solely on the assumption that the failure is only because the tensile strain in the transverse direction reaches the maximum ultimate tensile strain of the composite. So, we have the expressions for epsilon 2 T u already we have done using while determination of the transverse tensile strength. So, epsilon 2 T u for a composite could be written like this, and E 1 could be taken from the rule of mixture, and nu 1 2 could also be obtained from the rule of mixtures. Okay. So, this is a simple model. However, this model does not go well with the practical experimental results. Therefore, a more rigorous model considering the fiber microbuckling has to be considered. We will see that later on. This is just to understand that a simple model where the failure is due to the transverse tensile strain. Okay. Next, let us discuss the determination of transverse compressive strength. So, again a simple model analogous to the transverse tensile strength could be used. However, you can see that this is the transverse, just we have replaced the tension by compression, and the same equation, if you remember that for the transverse tensile strength it was epsilon 2 T u, this part was same and it was epsilon m u, just replace this by compression we get this. Okay. And we can get the transverse compression strength following Hooke's law, multiplying this by E 2. Therefore, this is the expression for transverse compression, but actually this is a simple model. Again, transverse compression is actually complicated. The situation is complicated because there are two possible modes of failure. One is matrix shear failure, and then there is fiber matrix interface failure. What happens is, suppose if you take a, if you consider a suppose these are the fibers. Okay. So, naturally this is direction 1 and this is direction 2. Suppose it is in the direction 2, it is subjected to transverse load, okay, subjected to transverse compression, say sigma 2. So, because of this actually it might experience shear failure. That means, this cross section, if you look at this cross section at an angle of 45 degree, it might experience shear, and it may fail like this. Okay. So, from the analysis of some compression failure specimen, it could be observed that many times it is because of the matrix shear failure or fiber matrix interface failure. Under this, there may be failure at the interface of the fiber and the matrix, and it might fail. Therefore, this simple model does not work out for determination of the transverse compression strength. However, this gives us a first hand idea of how the transverse compression strength is actually decided by the I mean, if it is only because of the transverse tensile strain in the matrix, how it is actually influenced by the fiber properties and the fiber properties and the matrix properties and the relative volume fractions. Next, in plane shear strength tau 1 2, again we take an RV, a simple RV, and suppose it is subjected to pure shear, it is subjected to pure shear as shown here. This is actually subjected to pure shear tau 1 2. Therefore, under this, if you consider that this is the shear deformation, of the composite. Okay. Suppose delta C is the shear deformation due to tau 1 2, okay. Delta F is that for fiber, and delta M is that for matrix. Okay. So, you can see that we have done that earlier also. Suppose we have a fiber and say matrix, suppose this is the fiber and this is the matrix. So, the shear deformation for the fiber will be of course different compared to that of the matrix. So, this is the total shear deformation, okay, because the shear modulus is different. So, this is the total shear deformation delta C, and this is for delta F, and this is for delta M. Okay. Therefore, the total shear deformation of the composite is nothing but delta C is equal to delta F plus delta M. Okay. Now, using the definition of shear strain, so suppose gamma C is the shear strain in the composite, I mean in this RV here, gamma F is that in fiber, and gamma M is the shear strain in matrix. Okay. Then going by the definition of shear strain, so gamma C is nothing but, say this is our equation number 1, gamma C is nothing but actually it is at tan theta. So, gamma C is nothing but delta C by S. Okay. This is S, same thing there we have shown two fibers where each is d by 2. So, gamma F is delta F by d, and gamma M is delta M by S minus d. Okay. So, using this in 1 implies S into gamma C is equal to d into gamma F plus S minus d into S minus d into gamma M. Therefore, we can write the strain in the composite gamma c is equal to d by s gamma f plus 1 minus d by s gamma m. Okay. This is equation number 3. Now, we have assumed that this obeys Hooke's law. Therefore, following Hooke's law, now the stress, in plane stress tau 1 2, because it is a pure shear applied on the composite. Therefore, the composite, the fiber and the matrix, all of them actually experience the same pure shear. So, is equal to tau f is equal to tau m is tau c. C is the composite, which is nothing but tau 1 2. Okay. Now, following Hooke's law, we can write tau f as g f into gamma f and tau m as g m into, this is following Hooke's law. Okay. This is because it is the same stress, subjected to same stress, pure shear tau 1 2, which implies that gamma f is equal to g m by g f into gamma m. This is equation number 4. So, we can put equation number 4 in 3. Therefore, 3 and 4 implies gamma c, which is nothing but gamma 1 2, okay, is equal to d by s. Now, epsilon f is equal to g m by g f into gamma m plus 1 minus d by s gamma m. Therefore, gamma 1 2 is equal to d by s g m by g f plus 1 minus d by s gamma m. This is our equation number 5. Okay. Now, sorry, if we consider that the failure is due to matrix, meaning at failure at failure the shear strain in the matrix reaches the ultimate shear strain of the matrix. Therefore, which implies gamma 1 2 is gamma 1 2 ultimate of the composite. Therefore, 5 implies, put this in equation number 5, gamma 1 2 ultimate is equal to, let me see what was the equation, yeah, d by, okay. So, this is d by s g m by g f plus 1 minus d by s. So, this is gamma m ultimate. So, this is the ultimate tensile strain, ultimate shear strain of the composite in terms of the ultimate shear strain of the matrix and other properties and dimensions. Okay. So, this is equation number 6, again using Hooke's law for the composite. Therefore, tau 1 2 ultimate is equal to g 1 2 gamma 1 2 ultimate, implies tau 1 2 ultimate is equal to G12 into d by S Gm by Gf plus 1 minus d by S. Okay. Where we know what is G12, we have obtained using mechanics of material approach G12 in terms of the shear modulus of the fiber and the shear modulus of the matrix and the volume fraction, okay, which implies G12 is Gf Gm by Vm Gf plus Vf Gm. Therefore, tau 12 we can put this G 12 value Vm Gf d by S Gm by Gf plus 1 minus ds comma mu. So, this is the expression we get, the same thing here. Okay. This is the equation number 8, only thing that we have replaced the G12 by its value. Okay. And we have taken this using Hooke's law, meaning that if you plot shear stress versus shear strain, okay, at failure this is tau 1 to u and this is gamma 1 to u, this is nothing but tau 1 to u by G12 of the composite, the slope is nothing but G12. In fact, we can write this also in terms of tau mu and Gm. Okay. So, I will stop this here today. Thank you.